Hello and welcome back. This is video 6.2.2 and we are going to start discussing Gibbs free energy. Now there are several ideas for Gibbs free energy and this is actually just the first half of them. The next half will be in video 6.3. Okay, so our very first idea. There are two thermodynamic driving forces for any process. So that means that thermodynamic driving forces are going to make the reaction happen. So two things will make the reaction go forward. First is decreasing enthalpy. That means delta H will be less than 0, negative. And increasing entropy. Things tend to want to go toward more disorder, and they want to release energy. They want to release heat. When these two directions take place, the process is said to be thermodynamically favorable or spontaneous. Now, it's important to realize here that spontaneous doesn't mean instantaneous. It's not instant. Spontaneous just means the reaction will happen. What this doesn't tell you is anything about the speed. For that, you would need kinetics. So this just tells you, will the reaction happen? Yes or no. It doesn't tell you anything, again, about the speed. It could be the reaction might take place naturally over a very long time, like rusting, or it might be instant, like an explosion. Both of those would be spontaneous. When they are not, the process is thermodynamically unfavorable or non-spontaneous in the forward direction. Some important notes about this. When a process is non-spontaneous in the forward direction, it is spontaneous in the reverse direction. A non-spontaneous process may happen when coupled with another spontaneous process. This happens a lot in the cell, in biology. So if you've heard of ATP, you can couple the reaction of ATP with other processes that would normally happen and cause them to be spontaneous in the cell. While a process may be spontaneous, it may not happen if it's a very slow process, or it may happen over the period of thousands of years. So let's define Gibbs free energy. Gibbs free energy is denoted delta G, and it's defined as delta G equals delta H minus T times delta S. So we notice here we have an enthalpy term, we have a temperature term, and we have an entropy term, and that all together taken into account gives us Gibbs free energy. It represents the energy available to do work, and it has units of kilojoules per mole. Now, the free energy of formation of delta G naught of formation is the free energy given for 1 mole of substance. Free energy of the reaction, or delta G reaction, represents how the free energy of the system is changing in a process. And both of these are interesting, or we're interested in both of these. Delta G reaction helps determine the spontaneity of the ambiguous cases. So, in processes in which enthalpy and entropy are either both increasing or both decreasing. Because as we said before, if we have decreasing enthalpy and increasing entropy, we know it's going to be spontaneous, and vice versa. If we have increasing enthalpy and decreasing entropy, it's going to be non-spontaneous. But what happens when both increase or both decrease? So that's where delta G comes in handy. A reaction is spontaneous when delta G reaction is negative or less than 0, and non-spontaneous when delta G reaction is positive or greater than 0. Note that T is the Kelvin temperature. You always have to convert to kelvins. Also, while delta G and delta H are usually given in kilojoules per mole, delta S is usually given in joules per mole, so the energy units must be converted before calculations can be performed. So, in a nutshell, please pay attention to your units here. So to kind of sum this up over here, if we have a negative delta H and a positive delta S, our reaction is going to be spontaneous. If the reverse is true, like we talked about, it's going to be non-spontaneous. Now, if we have both negative, we're going to end up being spontaneous only at a certain temperature. So if we have delta H as negative, and we have delta S as negative, then we'll have a large negative number here, a negative number there. Positive plus a negative makes a positive. So this is only going to be true if if the temperature is a low temperature. So this is spontaneous. At low temperatures. And we'll have to calculate to see exactly what those temperatures will be in each case. And if the reverse is true, if we have a positive delta H, we're going to need a very negative term over here to overcome that positive delta H. So to get a very negative term, we're going to need a very high temperature here so we can have a very high negative number. So in this case, we're going to be spontaneous only at high temperatures. Okay, so that's our first idea. Our second idea, Gibbs free energy is a state function, and that means it only depends on the initial and the final conditions. It doesn't depend on the process that actually happens during the reaction. Just where you start and where you end up. That's a state function. So again, we have our delta G equals delta H minus T delta S, our equation for Gibbs free energy. We can calculate our delta G of reaction by taking the delta G of all the products and subtract them from the reactants like we have before. And again, we can use Hess's law as we've been doing before for enthalpy and entropy. Let's do an example. Consider this following process at 25 degrees Celsius. So here's our reaction right here. Calculate the value of delta G reaction given that delta H reaction is given to you at negative 198 kilojoules per mole. And the standard enthalpy, the change in the enthalpy of formation, entropy is negative 189 or 87 joules per mole times Kelvin. Okay, right now is a great time to pause the video and please do part A. All right, we're back. Let's get started by writing out our equation for Gibbs free energy first. Okay, so here's our equation. Really, we're given everything. So the only thing we need to do is plug in our values. So our delta H reaction was given as negative 198 kilojoules per mole. And we're going to subtract that from 298 Kelvin. At 25 degrees Celsius, we convert to Kelvin. Plus 273, we get 298. Times negative 187 joules over moles times Kelvin. So here's the point where we need to convert. Look, we're given joules, we need to be in kilojoules so we can have our units match. So I'm just going to convert right in line here. I know that 1 kilojoule is equal to 1,000 joules. You can also convert here by just moving your decimal place if you prefer. Overall, when you plug this into your calculator, you end up getting a negative value, negative 142 kilojoules per mole. So, will this reaction be spontaneous? Yes, because delta G reaction is negative. That will be spontaneous. It will happen at some point. Again, we don't know the speed, but it will happen. Okay, part B. Calculate the value of delta G reaction given the following delta G of formation values. Note that delta G of formation equals 0 for elements at standard state. So this was just like our enthalpy calculations. For example, O2 gas at standard state, a pure element is going to be 0. So please go ahead and pause the video and attempt part B. Okay, we're back. So for part B, we're going to do our products minus reactants of our delta G at standard state. So just writing that out, delta G at standard state of a reaction. I'm going to use brackets so I can keep these separated, equals 2 times the delta G, Gibbs free energy of formation, of SO3. And I'm going to subtract that from 2 times the change in Gibbs free energy of formation for SO2 plus 1 times oxygen. But again, oxygen is a pure element and we're at standard state, so that's going to be 0. Okay, plugging in all of our reactions here, all of our numbers, I end up getting 2 times negative 371. Don't forget your signs here. That's where a lot of students end up messing up, is just mixing up all these signs, especially when you have negative upon negative. Swapping your signs around. Minus 2 times negative 300. And we can just leave this last term out because we know it's 0, so it doesn't influence anything at all. So our delta G of reaction, our Gibbs free energy, again works out to be negative 142 kilojoules per mole. And we'll see that that's the same that we got for the last problem here. So we know we're doing this correct. And again, this is negative, so this is going to be a spontaneous reaction. Again, I'm just going to reiterate, doesn't tell you how fast the reaction is going to happen. We'd have to use kinetics for that. This just tells you that it will happen. It's favorable. Okay, last part, a Hess's law problem. So part C, calculate the value of delta G of reaction given the following reactions. So again, we have reaction 1, 2, and 3. You are going to try to rearrange these, so reverse them, double them, do whatever you need to do to make sure that this matches your original reaction right up here. So this is the reaction where you're trying to match. So I'll give you just a second to please pause the video and go ahead and attempt part C. All right, we're back. So for the very first reaction, I noticed that I need to reverse this reaction because I have my reactants where I want my products to be and my products where my reactants are. So I want my SO2 to be in the reactants here. It's in the products. I'm going to flip it. So I'm going to reverse reaction 1. Reverse 1. And when I do that, I'm just going to write out my reaction in the reverse format. 2 waters plus 2 SO2 is going to yield 2 H2S plus 3 O2. And when I do that, I need to also reverse my delta G. So the negative delta G, or negative G1, delta G1, I'm just going to save some space, equals positive 1006. It was negative, so we're flipping that sign. Okay. For my next reaction, I notice that I need to reverse this because look, SO3 is on the wrong side. I also notice I only have 1 SO3 and I need 2. So I need to reverse and double reaction 2. Reverse and double reaction 2. All right, doing that and just writing it out. 2 sulfuric acid gives us 2 waters plus 2 SO3. And I need to multiply delta G2 by negative 2. Doing that, I get positive 164. My last reaction, I want to get rid of my H2SO4 that I've put on my my reactant side now. So to do that, I need to make sure that this stays in the same orientation because I can only cancel on opposite sides of the arrow. But I notice I have 2 of them here. This reaction only has 1. So I'm just going to double this reaction without reversing anything. So writing this out as double, we're going to redouble the entire reaction, not just the part you're interested in, just like algebra. And I always like to line my arrows up because I think it's a lot easier to just keep track of everything. And 2 times G3 is going to give us, don't forget, you're not changing the sign, so you're just doubling this here, negative 1312. All right, just checking our reactions to make sure that we can cancel what we need. So canceling out all the things we need to cancel out. H2SO4s, those are gone. H2Os, also gone. 2H2S, also gone. We have 3 oxygen here, 4 oxygen here, so now we'll just be left with 1 of them. So overall my reaction is 2SO2 plus O2 yields 2 SO3. And that indeed matches what we were trying to find. So now that we've checked here, we know we can add these up and we'll get our correct delta G. And when you plug this in, as no surprise, you're going to get the same value, negative 142 kilojoules per mole. And again, that is going to be spontaneous because that is a negative. Okay, that is it for video 6.2.2. I will see you next time with video 6.2 or 6.3.1. Bye, everybody.